Howdy, we're going to learn how to assign oxidation states. Remember, an oxidation state is simply just the charge of a compound or an element. And we've already actually kind of been doing this when we've been naming our compounds. So remember, I asked you before to name iron 3 um, oxide. Okay, and we know that since there's a Roman numeral 3, the oxidation state of iron is a positive 3. And I know that the oxidation state of oxygen is a minus 2 because it's in the 16th group and all those are a minus 2. And that's basically what we've done before. And so whenever we have looked at this, I taught you to take iron with its 3 plus charge, and then oxygen with its 2 minus charge, and then just crisscross the numbers and drop the charges, right? And we ended up with Fe2O3. Now, what we'll find out today is that those oxidation states still change even though we cross them out. So Fe2O3, iron, actually still has a plus 3 charge, and oxygen still has a minus 2 charge. And I'm going to show you a neat little trick for assigning these states. So there's several different rules, and I won't read all the rules. I will just go out uh, explain the examples. So for number 1, the rule says that anything by itself is an oxidation state of 0. So iron here is going to have an oxidation state by itself as 0. Now, if there's a diatomic element, it's still an element by itself, so it has an oxidation state of 0. Rule number 2 says that anything that's in solution or something that's an ion but it's still by itself says that it's going to have the oxidation state already given, which is 2 plus. So my oxidation state is a positive 2. Okay. And down here, rule number 3 says that the oxidation state of oxygen is always minus 2, with the exception of if it's hydrogen peroxide, which is going to be this. If it's a peroxide like hydrogen peroxide, then it's going to be a minus 1 instead. But that's the only exception. Number 4 says that hydrogen always has an oxidation state of positive 1. So um, remember that oxygen was still a minus 2, and we name that one, and we do that one first, and then we do hydrogen, which is a positive 1. Okay? And then, except when hydrogen is acting is bonded with the metal instead. So it's going to be a minus 1 instead. Rule number 5 says that the sum of the oxidation numbers has to be 0 in a neutral compound. So here I have a neutral compound because there is no charge right here. There's nothing sitting up in the top right corner. So all the oxidation states have to add up to 0. So I know that oxygen's a minus 2 from the rules before, and I know that hydrogen is a positive 1 from the rules before. So if I add these two numbers up together, I should equal 0. Well, that positive 1 minus 2 doesn't equal 0, but there are 2 hydrogens, right? So it's 2 times 1 minus 2 does equal 0, so that one works, okay? Now, if it's an ion, something like nitrate, then everything just has to equal the charge of the ion instead. So instead of equaling 0, everything's going to equal minus 1. So I'll actually move that up here, minus 1. So oxygen was a minus 2 charge, and there are 3 of them. So that actually makes the whole thing a minus 6. And nitrogen is going to be Nitrogen actually has to be a positive 5 for this to work out. And I'll show you an example of how to work this out right now. So all these are on your notes, just already here. So I'm going to go through all the examples that are listed right here. Calcium chloride is, first I need to assign oxidation states for oxygen, then hydrogen, and then if there's none of those, which there aren't any in this example, then I need to do a halogen. So my halogen for this one is chlorine. All halogens are going to be a -1 charge. Well, there are 2 of them, so I take that 2 and multiply by -1, and that means that chlorine has a total oxidation state of -2. Now, that means that since the other one all has to equal 0, since this is a neutral compound, this has to be a +2 here. Okay? And since there's only one calcium, that means that calcium's individual oxidation state is a +2. So the numbers that I want to pick for my examples and the actual oxidation states are those first ones right there. You don't want to take the totals, which would be these. These would be the totals. You want to take the individuals. Which is the first line. So my answer is going to be a +2, and my answer is a -1 for that one. All right, so for another one, hey, now I do have oxygens first, so oxygen is a -2. There are 3 of them, so oxygen is actually brings a total charge of -6. Hydrogen is a +1, but there's only 1 of them, so that's a +1. This is a neutral molecule, so everything has to be 0. So now that means that 1 plus what number minus 6 equals 0? That would be a +5. And there's only 1 of them, so nitrogen must be a +5. So again, you want to take these numbers right here. So hydrogen is a +1, nitrogen is a +5, and oxygen is a -2. Again, with water, oxygen is a -2, and then hydrogen is a +1. That's pretty simple. We can tell that -2 and then a +2 right here does equal 0, so everything checks out. So hydrogen is a +1, oxygen is -2. For this one, we've got an ion here, so everything has to equal the charge of the ion. It's not too bad. Oxygen is a -2. There are 4 of them, so there's going to be a -8. And everything has to total up to a -2. So that means that this number has to be a +6. So that 6 minus 8 equals -2, is -2. So there's only one of these here, so this has to be a +6 here. So sulfur is a +6 and oxygen is a -2. And then we've got a neat little trick right here that, and it's not actually that bad if you know how to break it up. So we have ammonium carbonate. Well, we have 2 polyatomic ions here. And so, but I already know the charges of the polyatomic ions if I treat them individually. So I have NH4, which I know is a +1 charge. You memorize that, or you know where to find it on the periodic table. And CO3, carbonate, is a -2 charge. So if you split those up individually, you can find things out pretty fast. So I'll just write CO3 is a -2 charge. Well, that means that 3, let's see, oxygen is a -2 charge, and then there are 3 of them, so that's a -6, and they all have to equal -2, so that means that carbon must be a +4. So I'm going to write these down. is a positive 4 and a minus 2 charge. Sorry, this has to be a positive 4 as well. And so for this other one, for ammonia, I'll write it over here. Ammonia, it all has to be a positive 1 charge. So hydrogen, we know, is a positive 1 charge. There's 4 of them, so this is a total of positive 4. And it has to equal a positive 1, so that means nitrogen is a minus 3. There's only 1 of them, so the individual charge is minus 3. Piece of cake. All right. And now you may be asking yourself, if I clear this off, you may be asking yourself, hey, does this 2 really count? And the answer is no, because remember, the whole total charge of it was 0. So that means that since there are 2 of them, there's 2 positive 1 charges, which cancel out this minus 2 charge, which makes this charge of 0. That's the real answer. So example number 2, this will lead us into the next lesson, is to do something like in a whole reaction. This is pretty simple. You just do, instead of doing individual elements or compounds, we'll just do them all. So iron is by itself, so it's a 0. And then oxygen is by itself, so it's a 0. Do the coefficients matter? No, not when we're assigning oxidation states. So just, you can ignore the coefficients. Oxygen is a minus 2. There's 3 of them, so it's a minus 6. And so then this has to be, the whole thing has to equal 0, so this has to be a positive 6, which means that 2 times what number equals 6? That would be a positive 3. Very nice. So iron's oxidation state, let's see, iron's oxidation state on the left side is 0, but on the right side it's a positive 3. And oxygen's oxidation state on the left side is 0, but on the right side it's a minus 2. So the oxidation states change, and this is exactly what we'll talk about in the next lesson. This is a redox reaction where the oxidation states change. And so now your homework is to do the front page of this, questions 1 through 10. Just assign the oxidation states on your redox reactions worksheet. Thank y'all.